Hi everyone, welcome back. So in the last few lectures, we took a bit of a detour and discussed antennas and arrays from a practical perspective, but we would like to return to the more rigorous part of the class where we discuss the mathematics behind some more advanced topics. So this is not the end of antennas discussion. We'll essentially build some more tools and techniques to analyze more complicated antennas and things like method of moments, integral equations, finite element. We want to get a bit deeper into the into antenna design and analysis. So today we will start with something that's very important in electromagnetics, really in differential equations, which are called Green's functions. Yeah, we've kind of seen this a little bit before, but today we'll do it more formally. Green's functions, and this will give us essentially today at the end of the class, we'll see where the radiation boundary condition in HFSS comes from. We'll try to kind of derive something similar to that, and we'll see what it is. Okay, so we'll start with this notion of Green's function. So what is a Green's function? So given a differential equation, let's say it's some differential equation which is acting on some function f, right? And on the right-hand side, I have some forcing function capital F, R. Then the idea behind Green's functions is to say that I can solve this differential equation, call it G now, the same differential equation D. So it can be the wave equation, it can be Laplace's equation, it can be Poisson equation, it can be Helmholtz equation, it can be diffusion equation, it can be anything, right? They all have Green's functions of their own. So I'll solve it with a delta function on the right-hand side. Okay. So what's the idea here? So the forcing function can be, let's say if you're in electromagnetics and you have the wave function, the forcing function is some kind of current distribution everywhere, right? And then we know that the vector wave equation, the magnetic vector potential satisfies an equation like this, or it could be charge density. And then the scalar electric scalar potential satisfies the wave equation, right? Where the forcing function on the right or the source function on the right is a current or a charge distribution. The idea behind Green's functions is to say that as long as this differential equation is linear, all I need to do is to solve it for a single point source or a point current. And then once I have that solution, which is known as the Green's function, then I can integrate that over all points to get the solution for an arbitrary distribution. So it's the same idea behind, it's exactly the same idea behind impulse response of a linear time invariant system, right? So from signals and systems, we have something called impulse response, right? So if I include an impulse on the left, then the response of my system is called the impulse response. If I have a complicated signal, I can just treat it as like a summation of different time shifted impulses. And then the output at the end is then the convolution of my impulse response with the input signal. Right? And that's the idea, is that once you have it for an impulse, you can shift it and then add them up. And that's exactly what a convolution is. Right? So once we have the Green's function, all we need to do is to convolve it with the source function, and that will give us the full solution. Okay, so that's why Green's functions are very popular in solving differential equations. They're a very general way to solve any differential equation. Okay, so in the past, we've already looked at solving the wave equation, but we took a slightly heuristic approach because we introduced at one point the fact that we know Coulomb's law to find what the solution is. But today we'll take a rigorous approach where we don't know anything about Coulomb's law. We want to solve the wave equation directly. Okay, so since we're in time harmonic case, the wave equation we've seen becomes the Helmholtz equation, and that's really what we want to solve. Right, so the equation is something like this. Laplacian of G plus K square G equal to delta of R. Right, that gives us the Green's function, but we'll put a minus here just because the solution we would like it to be positive. Okay, so just as a reminder, call that delta of R. So this we did in lecture 0 is delta X, delta Y, and we've also seen this before, if not in lecture 0. It's 1 over rho, and cylindrical coordinates, it's delta rho, delta phi, delta z. And that's the same thing as 1 over r squared sine theta, delta r, delta theta, delta phi. Right? Okay. So since we have spherical symmetry, from spherical symmetry, we can easily show that delta cannot be a function of theta and phi. So it's only a function of r. Right? And it's equal to delta of r divided by 4 pi r squared. Okay, and the reason behind this is that we want the integral of the delta function to be unity. So if I integrate from 0 to r, 0 to 2 pi, and 0 to pi, delta of r over 4 pi r squared sine theta d theta d phi dr, this is equal to 1. Okay, because the r squares cancel, and then integral of sine theta is 2, integral of d phi is 2 pi, so that cancels the 4 pi, and then integral of r from the delta of r is 1. Right, so this is the reason that in spherically symmetric problems, delta of r vector is just delta of r divided by 4 pi r squared. Okay, so then we can rewrite the wave equation in spherical coordinates. So the Laplacian becomes 1 over r squared d over dr, r squared dg of r over dr. That's the spherical coordinate function version of the Laplacian. K squared g of r is equal to minus delta of r over 4 pi r squared. And so we just made a substitution. And now what we can do is we can essentially multiply with r on both sides, and you can show that 1 over r d over dr, r squared dg of r over dr is equal to d square over dr square rgr. And you can expand both sides using the chain rule, and you can see that. It's not very hard to show. So because of that, you can rewrite the wave equation as d square dr square rgr plus k square rgr is equal to minus delta of r over 4 pi r. And we multiplied r on both sides. Okay, so since we have a differential equation now, this is pretty easy to solve, that when r is greater than 0, the solution should be for the homogeneous form, which has 0 on the right-hand side. And we know the solution to that is nothing but rgr is equal to a1 e to the ikr plus a2 to the minus ikr. Yeah, I can essentially write this as divide by r on both sides and then get rid of this r. Right, so that's the general solution for r greater than 0. Right? Okay. So here's where the physics kind of comes in. It says that since we know that the source is at the origin, so if this is a coordinate system, we have a source at the origin, this can only produce outgoing waves that are going out. And in this problem, when you have a source at the origin, we know we can't support an incoming wave because we don't have any other sources. Right? So we use that argument to say that A2 must be 0 because this is an outgoing wave. Sorry, this is an incoming wave. Outgoing wave. This is this is an incoming wave, and this is an outgoing wave. Because the phase is increasing as r is increasing, so it's propagating outward. Okay. So based on that argument, we now have that g of r is nothing but A1 e to the ikr over R. Right, and this is exactly what we had in the past as well when we tried to solve the wave equation where we got the retarded potential. So of course you take the Fourier transform of that, it'll give you this. Or the phasor version of that is this. Right, but now earlier we said that A1 is 1 over 4 pi and that comes from Coulomb's law, but we want to actually solve for A1 rigorously. So that's what we'll do now. Okay, so we want to answer the question, what is A1? So to answer that question, we'll start with the wave equation again and then integrate it over a volume. So wave equation is Laplacian of G, which is the divergence of curl of G plus k square integral over the volume, G of R dV. So I can write this also as dV equal to -1 because we're integrating the delta function. And then I can apply divergence theorem, gradient of G of R dV plus k square volume integral G of R dV equal to -1. Okay, and since we know that G of R is nothing but A1 e to the ikr over R, you can easily calculate the gradient in spherical coordinates. And that would only have one term. And because there's no variation in theta and phi, so it's just A1 e to the ikr over R times R hat. Okay? So we'll say S is a sphere. Let's assume S, the surface S, is a sphere of radius R. Then what happens? Then this integral on the left-hand side over the closed surface is nothing but d over d capital R, because now we're on the surface, not in the whole volume. So R equal to capital R on this surface times A1 e to the ikr, capital R, over R. Since we're on the surface, ds vector, so this should be dot with ds vector, right? This is a gradient on the left-hand side. ds vector is nothing but r hat times ds. And since even gradient of g has r hat, the dot product of those two things goes away. And then you're just left with ds. Right? Plus k square, again, volume integral g of r dv equal to -1. Okay. All right. So now what we can do is we can essentially pull this whole term outside the surface integral because this has no relationship with theta and phi. And the surface integral is really over theta and phi. So you're essentially just integrating the surface, just surface integral of 1 ds. We know that is nothing but 4 pi, right? That's the solid angle of a sphere. So this gives us A1 ddr e to the ikr over R times 4 pi R squared. Right? Because ds is not just d theta d phi, you also have R squared in there. Okay? Plus k square. And again, I can write e to the a1 times e to the ikr over R. And now that is integrated over, so let me actually write that out. So here I have a1 e to the ikr. This is small r now, or little r, because this is over a volume, right? So since this is only varying in In R, I can pull the theta and I can evaluate the theta and phi integral part of it. That gives me 4 pi. And then you have an A1. Then you have 0 to R e to the IKR times dr. And this R came from the fact that this integral here has R square sine theta d theta d phi, right? D phi dr. So that R square cancels with this, and then you get an R in the numerator. Okay, so this is equal to -1. Okay, so you can evaluate this whole thing. Take the derivative on the left-hand side. You have to only compute the derivative of this term, by the way, right? And then you integrate this integral using product rule for integrals, and you end up having something pretty simple. You will get minus A1 e to the IKR times 4 pi plus A1 R IK e to the IKR times 4 pi plus K square 4 pi A1 e to the IKR over IK plus 4 pi A1 e to the IKR minus 4 pi A1 equal to -1. Okay. All right. So clearly these two terms cancel out, this one and this one. And then you're left with all terms that don't have any r's in the denominator. Right. So then what you can do is you can take the limit as r goes to 0. Then all these terms go away. This term goes away. This term also goes away. The reason that goes away is because you have an r, which I forgot to write down. Okay, so both these terms go away, basically, and you're only left with this, right? And that gives you nothing but A1 equal to 1 over 4 pi. Okay, so once you have that, we know what the exact Green's function is, which we saw earlier, but now we've kind of derived it rigorously, right? E to the IKR over 4 pi r. So this deserves a nice box. It's not a very nice box. Okay. Now we've done this before, where if I have a general point, then I can just do e to the r, e of r comma r prime, where r prime is the source point and r is the observation point. That becomes e to the ik r minus r prime divided by 4 pi r minus r prime. Okay, and this is the scalar Green's function for free space or a homogeneous medium. You can just change mu and epsilon when you have a point source at r prime and your observation point is at r. Okay, so it's important to note that g of r comma r prime is equal to g of r prime comma r. And so what does that mean? That means that if you interchange the source and observation points, you get the same solution, right? It doesn't matter. And that's loosely speaking what is reciprocity, known as reciprocity. We'll derive reciprocity rigorously in the next lecture, but you get a kind of sense of it already, right? But this is of course in free space, but reciprocity is way more general than that. Okay. All right, so now that we have the Green's function, the next thing we want to develop is called Green's theorem, which will help us get to the boundary condition that we're looking for next, the radiation boundary condition. Okay, Green's theorem. So what does Green's theorem says? It says that if I have two scalar functions, P are scalar functions of position or scalar fields, right? Whose first and second derivatives are continuous. In this volume V, okay? And on the surface of the volume S. Then they satisfy this relationship, which is the volume integral psi Laplacian phi minus phi Laplacian psi dV is equal to the surface integral psi d phi over dn minus p d psi over dn. This is, I mean, the correct way to pronounce them, I guess, is something like phi and c, but I'll just say phi and psi because that's what I'm used to. But anyways, okay, so this is what we have. We want to prove this. So this proof is not very long, so I'd rather do it here and skip it. So let's do the proof. Okay, so the first thing we can do is we can use divergence theorem to establish one relationship, which is that the divergence of psi gradient of phi p dv is equal to surface integral of psi grad phi dot ds. Right? That's just the divergence theorem. And we also know that gradient of phi dot n hat is nothing but d phi over dn by definition. And that's something we saw in lecture 0. Right? It's the directional derivative along n hat. That's what the gradient really means. And then we also had the divergence of a scalar function times a vector function. So here the vector function is grad phi, is psi Laplacian of phi plus grad phi dot grad psi. So this is also something that we've seen in the first lecture 0. It's sort of a reminder. Okay, so now what we can do is we can start from this one and take a volume integral on both sides. So then that would give you, then this term becomes this, and then we apply divergence theorem. Right, so that gives us what? So the right-hand side becomes volume integral gradient phi, gradient c, dv, plus volume integral psi times Laplacian of phi dv is equal to closed surface integral psi gradient of phi dot ds. Right? Okay, and the rest of the proof is trivial. You replace psi and phi, and then you subtract. And that completes the proof. So what does that mean? If I replace psi with phi, then this term remains the same. This term becomes phi Laplacian c, and this term becomes phi gradient c. And then I subtract those two equations, then this term goes away, and then you get exactly this relationship. Okay? All right. So now that we're done with the proof, we can move on and actually use it. So now we want to derive the radiation boundary condition, and that is called the formal solution of the Helmholtz equation. Okay? All right. So we have two wave equations. So we have one that is satisfied by the Green's function. And we have one wave equation satisfied by the potential. Okay. And we want to find a solution for a bounded region. So we solved the wave equation for an unbounded region, and we want to use that to find a solution for a bounded region. right? Because we want to apply essentially a boundary condition on a bounded region, right? So what's the idea behind the radiation boundary condition? Maybe we should discuss that. So we've seen that there exists a solution for all of space given a current distribution, right? We can find the field or the potential at all points in space. But when you actually want to compute something, let's say in HFSS, you don't want to compute a very large space, right? So given an antenna, I only want to compute this region without having to know what the field is on the outside. I only want to know what the field is inside this region, right? So the question then becomes, what kind of boundary condition do I need to impose on this outer boundary? So what kind of boundary condition do I need to impose on this outer boundary such that this field inside is equivalent to the field there when you don't have any boundary, when you have an infinitely large solution. And that's what we want to establish. What's the boundary condition that lets us do that? So essentially, we want to apply a boundary condition such that when this field reaches this boundary, right, it doesn't reflect anything back. So there is no incoming field from this boundary. We want to make that contribution go to zero. Okay, so it's essentially, in one way to think about it, is that it's the boundary condition that doesn't allow any incoming fields. Okay. How do we do that? Right, so we'll make use of Green's theorem. Since we have two scalar potentials, G and phi, we can now apply Green's theorem and start from there. Okay, so Green's theorem implies volume integral G Laplacian phi minus phi del square G dV is equal to closed surface integral G d phi over dN minus phi dg over dN ds. Right? Okay. So the left hand side is equal to. So now what I'll do is I will substitute the Laplacian values from these two equations into this one and this one. So that gives me, on the left hand side, I have volume integral minus k square g phi minus g rho over epsilon. This is what you have on the right hand side here, right? Plus k square tg plus p delta dv. Okay. Now, of course, these two terms cancel out. And then that becomes, so this is nothing but equal to the right hand side. Right, so the right hand side is this guy. Okay. All right. So when I take an integral, so this term here, this term here is what? It's volume integral P of R this term delta R minus R prime dV, right? And that dV is over R. So which means that this whole integral only fires when R equal to R prime. So that term becomes nothing but phi of R prime, right? So we pull that out. Essentially, that comes out of the integral. So you end up with phi of R prime minus 1 over epsilon volume integral rho of R g of R comma R prime dV equal to the right hand side. Okay. Now I can pull this term to the other to the right hand side, and I can write it as phi of R prime is equal to 1 over epsilon volume integral rho of R g of R comma R prime dv plus closed surface integral g d phi over dn minus phi dg over dn ds, right? And then what we want to do is we want to make a change of notation where we replace r and r prime because we really want to going after phi of r rather than phi of r prime, right? So once we make that change, we get phi of r is 1 over epsilon integral over volume rho of r prime. So look very nice. Rho of r prime g of r comma r prime. Of course, this doesn't change because it's the same whether you write g of r comma r prime or g of r prime comma r. dv prime plus surface integral of g of r comma r prime d phi of r prime over dn prime minus phi of r prime dg of r comma r prime over dn prime or ds prime. Okay, so let's maybe take a break here and try to interpret what this is. So if you remember, this is exactly the solution for the free space case, right? This is the free space solution. So if you recall, we said that phi would not be 1 over epsilon integral rho e to the ikr minus r prime over 4 pi r minus r prime. And that's nothing but the Green's function. So this is exactly what we had for the free space case, right? So essentially, by adding a boundary, we have a contribution from the boundary, which is exactly over that boundary, right? So what is this saying? This is saying that if I have some boundary and I have some source inside, let's say, and I want to find the field here, right? The field here depends also on what the field is on the boundary. And this is the scalar field, right? So to solve for phi, you need to solve essentially this integral equation. This is not just an integral. It's an integral equation, which means the unknown is outside and inside the integral, right? And that's what makes it hard. But what we're interested in is only the free space solution, which is this one, right? So essentially, if we impose this as the boundary condition, so this being equal to 0, if we impose that boundary condition, then we know that the solution is equivalent to having a free space everywhere. And that's what we want to do. Okay. So this is, just move on. So that's the free space solution. So I'll call this term on the right I, which is the surface integral of g d phi over dn prime minus phi dg over dn prime ds. Okay. All right. So to make this term 0, what we want to do is we want to select S to be a sphere. It's not a very good sphere. So S is a sphere. We have some source distribution here, rho, right? Let's say this is the center of the sphere. We're interested in an observation point R when here we are considering the source point to be on this surface S, right? And we're sending this surface off to infinity. It's very large, essentially. Which is R prime is much larger than R. Okay, so this is kind of the opposite case where we have the observation point close by and the source point very far away. Okay, so under this approximation, you can say g of r comma r prime is approximately equal to e to the ikr minus r prime divided by mod r prime, right? So since r prime is much greater than r, we've approximated this part. Okay, and the other assumption is that n hat is nothing but r prime hat, since it's a spherical surface. Okay, and n prime is R prime. Okay, so essentially we are left with calculating dg over dn prime, which is nothing but d over dr prime of e to the ik mod r minus r prime over 4 pi r prime from these approximations. And you can calculate that turns out to be minus of minus ik over r prime plus 1 over r prime square times e to the ik mod r minus r prime over 4 pi. And then we go back and substitute this term, which is this term. So we substitute that back in here, and we are left with, so we get I equal to approximately closed surface integral e to the ik mod r minus r prime over 4 pi r prime d phi r prime over dr prime plus phi of r prime times minus ik over r prime plus 1 over r prime square times e to the ik mod r minus r prime over 4 pi. Let me close this bracket. Times ds prime. Okay, where ds prime can be written as r prime square sine theta prime dr or d theta d phi, d theta prime d phi prime. And I'm writing that as r prime square omega prime. And just for notation's sake. One other approximation we make is that this term is negligible because you have 1 over r prime square plus 1 over r prime, right? So compared to 1 over r prime, when the surface goes to large distances, that second term goes to 0, right? We can approximate that. So making that approximation, we end up with I is approximately equal to closed surface over S prime, R prime, d phi over dr prime, minus ik phi, e to the ik mod r minus r prime over 4 pi d omega prime. Again, our original goal was to say that this should be 0. So the way to make that 0 is to set this bracket to 0, right? So implies that limit r prime goes to infinity, r prime of d phi of r prime over dr prime. And of course, you can't just make that bracket 0 because this is a limit process, right? So we need to include even this term in here. Minus ik phi of r prime. This whole thing should be equal to 0. And this is called the Sommerfeld radiation condition. Okay. So essentially, if you impose this radiation condition on the potentials on the surface, you don't have any contribution coming into the volume. Okay, and similarly, you can do this for the magnetic vector potential and the magnetic scalar potential and the electric vector potential as well. So I'll just write it for the magnetic vector potential case. Goes to infinity. right? Because they all satisfy wave equations. So in case of the vector wave equation, you can decompose it into three scalar wave equations and add them up at the end. In Cartesian coordinates, you can do that. And since each of them is a scalar wave equation, they all satisfy similar boundary conditions, so you can add them back at the end. Yeah, it doesn't need a box. Okay. Now, if you look at these equations, so let's say we look at this one, what kind of function actually satisfies this, right? So you can pretty easily show that functions of the form phi equal to some phi tilde of theta comma phi, e to the ikr over r, and a equal to some a vector tilde theta comma phi, e to the ikr over r. These are the kind of functions that satisfy these relations, right? Because if you substitute this into this condition, to this condition, then when you multiply with r, the denominator r goes away, and then you're left with this term. And then you take the derivative with respect to r, you get a plus ik, and that cancels with this minus ik. Right? So, but what does this actually look like? This looks like nothing but the radiation pattern of an antenna in the far field. That's what the potential is. From that, you can get the fields. But we know that the pattern varies as a function of theta and phi. And in the far field, it varies as e to the ikr over r. And we've seen that before, right, with many examples. So essentially, you get nothing but a canonical solution for a far field equation once you apply the radiation boundary condition. Okay, so now that we have A and phi, you can put them into the expressions that give you the fields from the potentials, and you can show that the fields satisfy a similar boundary condition, which is limit r tends to infinity, r of e to the r, e of r plus r hat cross theta h of r equal to 0, and limit r tends to infinity, r h of r minus r hat cross e of r over eta equal to 0. Okay, so these are sometimes called the Silver-Mueller. I think there's like a dot here. Absorbing boundary condition. Okay, and if you look at these fields, what do they look like? They are nothing but TEM fields, right? Because you see here that if EH and R are perpendicular to each other, EH and R hat are all perpendicular to each other, then they would satisfy both these expressions, right? So this is nothing but a TEM wave. And we saw that in the far field, waves satisfy TEM condition, right? Which means that the EH and R hat vectors are all perpendicular to each other. So it's nice that even from a rigorous derivation, you can show that in the far field, under the boundary condition, it's equivalent to saying that the fields are TEM, right? So this, of course, makes several assumptions. What are these assumptions? What assumptions have we made, right? So one was that we sent S to infinity, or the surface to infinity. Right? So which means we need a very large surface. And the second one was that that surface was spherical, right? So both are not really practical. Let's say in HFSS, if you want to make this surface, it has to be very large, first thing. And the second thing, it has to be spherical. And that's not always easy because then you have to use a spherical mesh and it becomes kind of complicated. So ideally, we would want something that can work for a rectangular or a kind of a cuboidal shaped, a cube-shaped surface, and at 90-degree boundaries between surfaces, right? So if we go back here and we look at these expressions, now I can replace h, right? I can write h as 1 over I omega mu curl of E, right? So that's just from Maxwell's equations, Faraday's law. I put that into the previous expression for the boundary condition, and you can show that the boundary condition looks nothing but it becomes exactly this. Tangential component of the curl of E is equal to IK times the tangential component of E. Okay, and you can kind of see that here. And if you put that expression into the first value, H becomes curl of E. R hat cross curl of E is nothing but the tangential component of it. And that must be equal to the tangential component of E. Because we know E is perpendicular to R hat. So E is nothing but tangential already, right? So this is an equivalent condition, but this is really an approximation because not an approximation, but this is a condition that's not really easy to impose because you need S to be large and also to be spherical, right? So this is called a first order boundary condition. First order absorbing boundary condition. HFSS uses something a little bit more complicated. It uses a second order boundary condition. We're not going to derive it here, but I'll just mention what it is. IK tangential minus I over K curl of E tangential plus I over K gradient of divergence of E. Okay, so we've added two terms here, these two terms. So what do? They account for oblique incidence, and S does not have to be very large. S can be lambda over 2 away from the source. Okay. So what does oblique incidence really mean here? So we said that, okay, when I have a big sphere and I'm very far away, then the waves are all normal to the sphere, right? In the far field, they kind of go, the field kind of propagates like this. But if I place a rectangular sphere now, if I make this rectangular, right, then I don't have normal incidence. Here it's normal, here is normal, here is normal, here is normal, but here is not normal, right? So you have like an oblique incidence here. So despite that oblique incidence, it doesn't produce any reflections, or the reflections are minimum by imposing the second order boundary condition. And this delta t here is nothing but the tangential component of delta. So if you're in the xy plane, then delta t would be ddx x hat plus ddy y hat. Okay. All right. So we haven't really derived this, but hopefully now you know where this term comes from. This part, and you can think of this part as a correction factor. so that you can make a rectangular air box that's like close to lambda over 2 away from your antenna. Okay. Okay. So these are not the only available boundary conditions. There are others. So I'll just mention them. So one is called the PML boundary, or the perfectly matched layer boundary. So what is that? That is essentially if I put a PML boundary on the surface, then it places a material. So this is not exactly a boundary condition. It's a material that is placed like that pads the entire structure. And this material is specifically designed to have material properties that absorb incoming radiation. So there's essentially some loss associated with it. So you have a wave that comes in, and as it propagates, it decays and dies out. So it's matched at this region. So there's no reflection at this location. And once it enters the medium, it decays exponentially. Right? So it's a really complicated kind of material property. It's anisotropic, it's lossy, and so on and so forth. So it doesn't really impose a boundary condition on the fields. It just tries to satisfy the boundary condition given a certain material property. Okay, so this can actually be quite nice. So in fact, HFSS recommends PML boundaries for antenna problems, as far as I know. Right, but the solution domain can be slightly larger because you have to also solve for the medium here, not just the air box inside. But the nice thing is that with PML boundaries, you don't have to be lambda over 2 away, you can be lambda over 4 away or so. So the overall solution space can be smaller. But from my experience, PML for most antennas doesn't make that much difference, and it can be a bit slower to solve with. So I usually just rely on radiation boundary condition, unless it's like a very specific kind of antenna that you need to be very precise with the simulation. Another boundary condition is called Febby boundary. And we'll see this later. So it's the finite element boundary integral. This is very useful when you want to solve subdomain problems. Right, so the idea here is that it's a combination of finite element and method of moments or integral equations. That's where the name comes from. So at the boundary, you essentially apply both FEM and MOM and try to find a unique solution that satisfies both conditions. So roughly speaking, that's what it is. So maybe once we discuss method of moments and finite element, which will be later in the class, this will make more sense. Okay, so these are the three basic boundary conditions. So we kind of summarize, we started with the Green's functions, and we did Green's theorem, and then we derived the boundary condition, the first order case, we derived this rigorously. And then we said, okay, in reality, it uses something a little bit more complicated. So we have a second order correction factor as well. Of course, you can also derive this rigorously, but didn't do that here. And then I briefly mentioned that there are other boundary conditions, and we talked about a little bit about what they are and how they're imposed. So that gives you a slightly more deep understanding of what's going on in these solvers like HFSS. So hopefully that's sort of interesting. If you have any questions, you can leave them in the comments below. If not, I'll see you in the next video. Thank you.